In this lecture, we learn about minimum shift key. This is in fact is the continuous phase modulation or the continuous phase frequency shift key. Actually, when we study the variants of QPSK, uh, we learn that we have the phase variations from 180 degree to plus minus 90 degree or plus minus 45 degree. So these phase variations cause invalid fluctuations which are not suitable for nonlinear amplifiers used in satellite communication. So to overcome this, we use the continuous phase frequency shift key. This is in fact is the OQPSK plus FSK version of the modulation. So we can say that to some extent it relates to OQPSK and to some extent it relates to FSK. So in FSK we used two tones. One is F1 for symbol 1 and F2 for symbol 2. Here we are using the same practice, but we are concerned about the initial phase of the symbol, because the initial phase of the symbol will help us to determine the phase at the end of the bit duration. So this is the phase at time 0, and we are also want to know the phase at time TB, which is the bit duration. So initially we consider that this is theta of 0. So the conventional form of the angle modulated wave is like this, that we have cos 2 pi fct plus theta of t, where fc is in fact is the arithmetic mean of the two frequencies f1 and f2 used here. So theta of t is in fact is calculated by some factor h. So this is also called the deviation ratio. So we can see that this is theta is linear during the bit duration, starting from 0 time to time t. So this is in fact is the value of theta of t, which will be determined during the entire interval of bit duration. Actually, h is nothing but TB into f1 minus f2. So we take this value of h is equal to 1 by 2. If we take the value of h is equal to 1 by 2 and this t is equal to TB, then the phase at TB time is plus minus pi by 2. So put the value of h is 1 by 2 and t is equal to TB, we'll get the value of theta TB is the initial phase value at the start of the bit, and the value at TB, which is plus minus pi by 2. So this plus minus pi by 2 depends that whether we are choosing 1 or 0. So in one case we have the plus pi by 2 phase change, and in other case we have the minus pi by 2 phase change. So that's very simple to recognize the phase at the start and end of the bit duration with the help of this formula, and we substitute the value of this phase here. So in fact, at 1, if we have plus pi by 2, and if 0 we have minus pi by 2, the symbol is modulated according to different phases in this formula. So first look at the trellis diagram of the uh, phase. So this is called the phase tree or the trellis diagram of the phase. So we have the so in this trellis diagram, we have the negative part as well, and we see that during the bit duration, it is linear. For example, if there is consecutive ones, so we have pi by 2, we have pi by 2, we have the pi h uh, radian, pi h radian increase, because we are taking the value of h generic. Here we are not considering it 1 by 2. We are taking it value is taking its value is h in the general form. So this when the bit consecutively once the phases goes on increasing up till 4h, and it goes on decreasing when we have 0 phase, and maybe in any other form it has some other structure. So if we assume that the value of h is equal to 1 by 2, which is very specific for MSK. In MSK, we assume that the value of h is 1 by 2. So the value is plus pi by 2 for symbol 1 and minus pi by 2 for symbol 0. In this case, we see the trellis structure. The trellis structure for a random bit stream 11010000 is, for example, first the 1 comes. So there is, it goes from 0 to pi by 2. So theta TV is pi by 2 now. Now theta TV is considered as the initial phase. And what about theta 2 TB? So it is again 1, and it increases pi by 2 and reaches the phase of pi. And then we have 0. So the 0 will decrease the phase minus pi by 2. And then we have 1, it increases the phase pi by 2. And for consecutively 3 zeros, it decreases minus pi by 2, minus pi by 2, and minus pi by 2. So this is the case with the phase only. And now we see that what will happen to the signal itself. You know, the signal is in fact is given by this formula, where Fc is the arithmetic mean of the two frequencies f1 and f2, and theta of t is split by the trigonometric identity. So we have the in phase component of the signal representing by this, and the quadrature phase component will representing by this equation. So we will see here that theta of t varies according to the trellis diagram, and correspondingly it depends on the previous data that how we modulate our signal. So it is not possible that we don't know the previous data and even then we are able to modulate the symbol. So how we modulate the previous bit, so it helps us to determine how we modulate the next symbol, because it determines the value of theta of t, right? So if t is equal to tb, then theta tb is equal to theta of 0 plus minus pi by 2, right? Because the value of h is 1 by 2 here. So I have already told you here. So now look at the waveforms. So there are four possibilities. That we have the in-phase component with plus minus 2 EB by TB cos pi h TB by T, and plus minus 2 EB by TB sine pi 2 TB by T. So in fact, we plot this in phase signal and this quadrature phase signal separately, and then we'll sum up the signal. So first we look at the possibility that here we have the initial phase is 0 at the start. Initial phase is 0 at time 0, and at time tb is pi by 2. So it means we transmit symbol 1. So if the initial phase is pi and theta dB is pi by 2, so it means it decreased by the factor minus pi by 2. So we transmit 0. And if it is pi and we have minus pi by 2 at so we take the transmitted symbol as 1, right? Because uh, here we have the initial phase is pi and theta dB is minus pi by 2. So we transmit symbol 1. And if it is 0 to minus pi by 2, so the transmit symbol is 0, right? So as we know that in frequency shift keying, these two frequencies are orthogonal. For this reason, the deviation ratio of 1/2 is referred to as minimum shift key. So now we go to the basis function. So these are the two basis function which help us to correlate the signal in phase and quadrature phase signal. So the SI of t is in fact the SI of t when multiplied by phi 1 of t plus S2 of t when multiplied by phi 2 of t will give you the value here. So you can see that these two signals are 2 EB by TB sine pi 2 TB by T, or with the plus minus sign. And similarly for the in phase component. So the next we relate these two equation. So look at S1 of t, S1 of t with plus minus, and SQ of t with plus minus, and psi 1 of t and psi 2 of t. So the S of t signal generated by S1 of t, theta 1 of t, S2 of t, theta 2 of t for 0 to TB duration, right? And for example, because as in OQPSK, we create the offset. So here we create the offset, and this offset is from 2 TB duration and spans from minus TB to TB. And in S2 of t, that duration is from 0 to 2 TB. So that is the result of this is EB cos theta of 0, and that is minus EB cos sine theta TB. So these two signals are offsets, and you can see that for input bit 1 and theta of 0, 0 plus pi by 2, so we have S1 and S2 coordinates are plus EB and minus EB. And similarly, we have the signal space characteristics of MSK. Also, if you see the decision region, so the decision region is also more or less like the QPSK. So we have the decision region Z1, Z2, Z3, and Z4. So if we just you can see the table pointed out here that this is in fact is the message point 1 in region Z1, and this is the initial phase and the final phase pi by 2. And here in all region we have the initial phase and the final phase determined. Also it is mentioned in the signal space characteristics of MSK. So this is the modulator structure. This is the modulator structure. As I've shown you that the phi of 1 of t is the basis function, and phi 2 of t is the second basis function. So the in-phase channel is integrating from minus TB to TB, and quadrature phase channel integrating from 0 to TB. Then we have the value of x1 and x2, and then we have a decision circuit. Then we have the logic circuit for the phase decision. So it will estimate the in phase, will estimate theta of 0, and this will estimate theta of TB, right? So this is how this modulator works. So this is this demodulator works. So this is the structure of the MSK receiver. So the error probability of MSK is similar because of the similar signal space diagram. So we ignore the component which is in fact is a scared component, and we can simply write it as the complementary error function of square root of EB by N naught. So the transmitter part, we have the in fact is this is the carrier component, and this is in fact is the cosine with h is 1 by 2, and depending over the value of t, which is changing from 0 to tb, and it goes on with the band pass filter to filter the frequency f1 and f2, and then we have the cross summation of the two signals, because when we are modulating it, in fact we are in fact we are using the signal, band pass filtered signal with f2, and we have band pass filter signal with f1. So in fact both are summing up here, and will give the basis function phi 1 of t. And here it is in fact subtracting the two signal to give the basis function phi 2 of t. Then we multiply the message 1, which is di of t and dq of t. So after multiplying with the message, we just sum up the two signals and generate the MSK transmitted waveform. So this is about the phase estimate of the signal at receiver. So I already explained this, that the in phase branch will estimate the phase at 0 time, and the quadrature phase branch will estimate the time at theta TB. So now look at this. The signal S1 started from minus TB, right? Minus TB time, and this signal is started from 0 time. So this is S1 phi 1 of t, and this is S2 phi of t. So the bits are in fact representing by the sign component. So we have this component for the 0, we have the positive part, and we have this component, right? And for phi we have negative, we have this component, and for phi negative we have this component, and for 0 we have this component. But when we multiply it, when we modulate it, so it will have the other part as well. So this is in fact is the carrier. So this generated carrier, this is the generated output which you are seeing inside the envelope, and these two waveforms are sum up to generate a waveform which are continuous in phase, which is the MSK waveform. So that is, in fact, I